All right. Hello, everyone. Welcome back. Hope you had a nice weekend. So today we want to continue talking about sensors, and we want to finish that. Uh, so there was like a little bit of a few slides remaining for the previous module before side channels. I want to finish that. And then there are a few things I want to discuss on the sensor security, kind of to finish this discussion. Hopefully we can, today we'll be done with sensor security. All right, if you remember, I was giving you examples, and the last thing that I was talking about is this attack uh, that what was trying to do is trying to remotely create some form of a fault. So the kind of the reason that I'm showing you this is in order to launch a fault attack, you don't need to necessarily be there to launch and change the physical operations. You can actually do it remotely, which is quite powerful. So the idea of the attack was that they were trying to create some faults by changing the operation of the CPU. And then these changing the operation creates some induce some faults that these faults then can flip bits, and then flipping those bits in some control fashion could cause the attacker to know the cryptography key. So how does it work? It's based on this main principle called dynamic voltage and frequency scaling, or DVFS. DVFS is kind of this software hardware framework which allows systems to save energy without sacrificing performance. DVFS is usually controlled by the kernel. And what it does is basically change the frequency and or the voltage in order to achieve different goals. Sometimes it's reducing it to save power. Sometimes it's increasing it to achieve performance. The reason that this works is that, as I showed you last time, power is has direct relationship with voltage and frequency. A squared relationship with voltage, and then direct relationship with frequency. So essentially, if I reduce voltage or frequency, I'm gonna get performance benefits. Unfortunately, if I do that, I'm gonna also increase the delays, which means that the performance will be decreased. As a result, usually most of the modern systems has kind of these pairs of voltage and frequencies, which kind of gradually go up. The idea is that I want to increase these two as the workload is kind of increasing. So if there are a lot of things that I need to do, I scale the voltage and frequency as high as possible so that I can kind of like clock as fast as possible and compute as fast as possible. Whenever I don't need it, I just drop it down, both voltage and frequency, or either of those two. And then this way I'm going to save a lot of power and energy. As I said last time, usually there are pairs of voltage and frequency. Typically, you don't like pick any arbitrary voltage or any arbitrary frequency. Usually, for most of it, there is some form of a specific frequent voltage that you always stay within that, and then you can gradually increase the frequency. But there are also some points like these are like very deep sleep modes that you really significantly reduce the voltage and then kind of semi shut down your system. If you want to stress test this, you can actually go a little bit higher. So actually, this kind of like a blue line, the blue curve showing that this is like the maximum that you can go. If you go beyond this point, which means that you increase the frequency a little bit higher than you should, or increasing the voltage, reducing the voltage a little bit than you should, then you're gonna get into this side of the curve, which is when the system start getting faulty. Okay. Um, and then this is device specific, so it's not like the universal line. So there are different devices as it's kind of different patterns. So it's not like a one thing that you always see that. So why there are these faults? The reason that there are these faults is that those of you who know a little bit about digital logic, digital logic has these two parts. This is what we call a combinational parts. These are just gates like AND gates, OR gates, NOR gates, and so on. And usually a combinational logic is sandwiched between two what we call sequential logics. These are flip-flops. Flip-flops essentially is the memory of the system. So think about this as kind of like a factory line, that there is a line, there is a belt. You put things in the belt, it goes through some process happening, and then you kind of store whatever happened, and then you go to the next one. So it's like a checkpoint-based system, okay? So you kind of like, you have a checkpoint here. You kind of do some things, then there's another checkpoint, do some things. For those of you playing games, like you play Call of Duty, you go a little bit further, it saves and you go to the next one, right? So this saves is essentially your flip-flops. It remembers all the things that happens prior to that. This way, then I can clock things, right? So every cycle of the clock, essentially, this is the amount of activity happening. The next clock comes in, things are stored here, and then the next one happens. So this way, I can actually clock it with some frequency and then let these things go. So how do I decide how fast I can clock? The fastest I can clock is actually the latency from here to here, right? Because essentially what I'm saying is that whenever the new clock comes, the data needs to go through this path and reach to this point before the next clock. If it doesn't reach to that point, then you cannot save the correct data, right? So whatever we are kind of sampling here is an incorrect value, right? So this is when things gets faulty. If I essentially clock it faster than it should be, then I'm going to lose some data. I'm going to get some random behavior of my system, right? And then the way this works with DVFS is that if I decrease the voltage, so if I bring down the voltage, this delay is impacted, so the time it takes from here to here increases, okay? Generally, if I think about it this way, if I put more voltage in, it means that I can increase the current, which means that electrons has more energy to go through the path. If I reduce the voltage, I'm essentially reducing the energy. That's why it takes longer for them to reach to the end of the path. Okay, so what will happen is that in correct systems, I can know how long these things, like these delays are. So when I reduce the voltage, I reduce the frequency accordingly, such that then if this thing is increasing, this path is increasing, I clock it slower, okay, which means that the frequency also goes down. And that's why there is actually kind of points like this. So basically the designers have measured these path, and there are millions of these paths, by the way. You usually just go with the worst, which we call critical path. So there are these paths, and you know that if I reduce the voltage by this much, the amount of delay that's going to increase is this much. So I reduce the frequency accordingly. Okay, so under right circumstances, nothing bad happens, and it's great. What will happen is that if I reduce the voltage but don't decrease the frequency, or decrease the voltage too much without accordingly decrease the frequency, then I'm going to start having this weird behavior. Okay, and what these guys found was that I can actually control exactly which bits is going to be flipped and to what number. Okay, so if I know exactly like the path, and let's say this path is some registers that I want to calculate, they show that this can be very deterministic. So I can actually kind of figure out what is the right voltage, such that if I want to see this number and then change this last 2 bytes to these numbers, I can. So that's kind of like the main innovation in this paper, that they show that this is software controllable by basically just modulating the voltage and frequency of the device. So then the rest is really, how do I use this? So kind of this is their basic block. They show that they can flip bits at their will with the numbers that they want, and this becomes a very, very powerful tool for them to actually do various things. So for example, they launch various different attacks. They launch a confidentiality attack, which, as I said, they try to find a AES secret. They also do some form of what we call privilege escalation, which the idea is that you kind of flip the bits that kind of give you more privileges. For example, you have root level and user level, and then if you flip that bit, then it's as if the data has some extra privileges, extra capabilities that you can do things. It's done under trust zone. Later on in this course, we're going to talk a little bit about trust zone and trusted execution environments. For now, don't worry about it. Just know that they can use this kind of capability in order to launch more powerful attacks. Okay. What are the defenses? There are both software defenses and hardware defenses. At the hardware level, you can actually limit the operation. So as I said, currently, at least at the time of this attack, the attacker could choose any arbitrary points in the voltage and frequency without any checks. And the assumption was that the actual user knows those points and never gonna not using those correct points. But unfortunately, if anyone can change those points, the adversary can change it to any arbitrary numbers. So that's one thing that you can do to make sure that you never at this voltage you can never go down a certain frequency and so on. There are other things that the author suggested, including creating different boundaries for different software. For example, if you have a trust execution environment in the regular system, the DVFS control of these should be at least different, so that even if the attacker can change things, it can only change it at the user level and not at the T level, and so on and so forth. You can also do randomization, redundancy, and all those things. So that's kind of like the basics of this attack that I wanted to finish because the last time we didn't have time. Any questions here? Cool. All right, so that's kind of it with part one of the sensor. We kind of talk about various different physical attacks, and the readings. We're also giving you a little bit more. So hopefully you kind of fully understood the kind of space in this domain. I want to kind of continue this discussion and talk about three new things. So first of all, the status quo currently is that, as we have seen in the past 2-3 weeks, computer systems are designed correctly, right? And we have strong theory behind them using crypto. And we can usually load a correct program without any issue through secure boot. But the problem is that since these computers, especially IoT devices and embedded systems that we are mainly focused on in this course, are constantly interacting with the physical world, they are susceptible to various different type of attacks, mainly sensor attacks, transduction attacks, fault attacks, and side channel attacks, right? And then these can be caused by their operations, just fundamentally how they operate. It could be caused by bugs, but most of the time it's just physics that causes these attacks, right? And as I said, the attacks could be different types of faults or different type of transductions. And we also talked about kind of different places that these attacks can happen. It could happen in the physical world or the analog world or the digital world, right? So today I want to talk about three more things about sensor security, such that we have the complete story. First, I'm going to talk about authentication and where sensors can be used for authentication and how the attacker can attack that. This is kind of another different vector for an attacker, and also I'm going to talk about some defenses in this domain. Then I'm going to talk about one emerging application that is augmented reality, virtual reality. Because that's where sensors and computation and actuations are very tightly integrated with the physical world. You're going to see that many of the attacks that we talked about kind of directly applies there, and there are some newer attacks that I'm going to talk about. And lastly, I'm going to talk a little bit about integration of machine learning on sensors. And again, this is something that is very, very rapidly growing, right? Because of the capabilities that we have with machine learning, okay? So let's talk about authentication, and I'm going to particularly talk about what we call distance authentication and authorizations. So where do we use these kind of capabilities? It's actually used in many places. For example, contactless payment is based on the sensor interaction between your credit card the chip in your credit card and some post, some receiver, right? The way that we're gonna lock and unlock our card most of the time, you never like use like a physical key. Is actually all about with that remote fob that you have. Similar with the smart locks, many automatic doors and screens, toll collections, any sort of access that you have in many labs and many offices that you use a card. So all of these are based on the notion of proximity, right? And then some handshaking of information between the two devices. Okay, so it's actually quite important and used very very widely in our lives. The key idea in all of these kind of distance-based, proximity-based protocols is that you use a communication, different signals, physical signals, as a means to kind of measuring the distance, okay? Because it's not all about just sending a request, like a cryptography request. You have to actually be physically there in order to do that, right? So for example, your key card does not work from 10 meters away if you send the request there. You have to be there and then do some actual physical measurements, okay? So under this system, there are attacks that can happen. And I want to ask you, what are the type of attacks you think can happen in the system? Let's say a key card, right? So think about like a simple key card. If you're an attacker, what can you do? Yeah.
Maybe impersonate someone.
Yeah, you can try to kind of copy the key card and then like you have another key card that impersonate, right? So that's like the most common type of attacks in the systems. There is a very good solution for that and using cryptography for it. So if you actually do, some form of a cryptography based solution where the secret key cannot be easily replicated, then you will have you can eliminate these type of attacks. So that's why most of these key cards is not easy to replicate, but there are attacks that shows that you can replicate these. So for example, attack shows that you can replicate like a remote controller and so on and so forth. But most of them are pretty secure these days because of the existence of strong hardware-based cryptography. What else can you do? So let's say I cannot duplicate the credit card. Can I do the access card? What else can I do? See if anyone else wants to say, but then I can ask you. Go ahead. Go ahead.
Oh, denial of service. Like you could prevent other people from selecting it.
Yeah, you can prevent other people. You can kind of destroy the pose or jam the signals. Anything else? There is this interesting attack called relay attacks, and that's the one we're going to talk about. So the idea of relay attack is that I cannot replicate the card, but here's what I'm going to do. So let's say, for example, this guy on the right owns this red car, okay? So he has a fob in his pocket, okay? But obviously, in order for an attacker to unlock this car, they have to somehow has the key fob. And they have to be in the proximity of the car. So you cannot if you actually kind of hit click the unlock button there, probably is out of the range of the car, so nothing happens. So even if the attacker has access to there, they cannot do it. But here's a very, very clever trick, which called relay attacks. So the relay attacks is like a two-person job. So there are two people attacking. The first person has an antenna, okay? What they do is that they force the car owner to press the unlock button. There are various ways that you can do this. But then what it does is that it doesn't do anything with the signal. It just takes the signal, relay it to some distance, okay? So essentially all it does is that this is a physical RFID signal. I'm going to just basically send this, I'm going to amplify it and send it over to another receiver who has another radio. And this guy, what he's going to do is that they're going to receive it and replay it. And what happens is that now we are kind of virtually, is as if the attacker has the key fob and is next to the device. We're not replicating anything. We're not breaking any crypto. We're not forcing the owner to be there or like physically stealing the key fob. All these two attacker does is just listening to that signal, relay it and replay it for the car. And this way they can unlock the cars. There are actually very cool videos on YouTube. Maybe during the break, I'll find some that they actually do these relay attacks and they can unlock doors and unlock cars. Even recently, people have shown that this is possible. So like one thing that many people say is that never put your key fobs near a window outside, near your car, because this is a very easy way for attackers to unlock these cars. Does that make sense? Anyone has any question here? Yeah.
This can be done just like one attacker as well, right?
What's that?
This can be done just one attacker as well.
Oh,
Like a line of sight from the target.
yeah, well, I mean, you need kind of two devices. You need one that is collecting the information from the key fob. You need to kind of transfer it to another receiver. This actually can work thousands of miles, right? Because all you need to do is that if I have a transmitter that is strong enough that can send this, then I can unlock it from like your car could be in Boston and still can be stolen. Yeah.
Would it be possible to somehow record the fob signal so you wouldn't have to like copy the fob, but if you got the signal somehow, you can just keep replaying it whenever.
Good question. So the question is, why don't we just record it so that every time we can do it? So that's actually, this is a known attack, replay attacks, and the main way to protect the systems against it is through using nonce. So your key fob never sends exactly the same signal every time. There is actually a nonce that every time it sends a slightly different signal. So same as cryptography. So the way that we never encrypt the same message over and over, we have some form of a counter. So this is actually the same.
Wait, how does the car know when to increment it? Because can't people like click the key fob like when they're out of the range of the car?
They can do the clicking. They're actually very nice. So this is actually very known problem in these systems. There are ways to fix that. There's this there is this paradox called, I forgot the name, Byzantine, I think. And this is a known problem for networks, for these systems. So the idea is that there's this like old problem, maybe you've seen it in your network classes, that there are two kings, they want to talk to each other, like there are two generals, they want to talk to each other, they want to attack a castle. The idea is that they can only attack the castle if they know exactly what time they attack. Okay, so they need to agree on a time to attack a castle. Okay, but the problem is that the mode of their communication is not secure, which means that if they want to communicate, they have to go through a lossy communication. Okay, and now how do we fix this problem? This is actually the basis of many network systems. There are various different solutions. I definitely recommend you to go and look at it. But typically there is, for example, one thing that solved this problem for this particular case is that I only look into future numbers. So like, for example, I never look into the previous, but like I not only check the next number, but I also check the next 10 numbers. So there are these ways that you can do it, but for key fobs, there are actually lots of different solutions. But this is the same problem with networks as well. For example, how do you know that the packet that you send has not been dropped, right? TLS, for example, has this problem. Any sort of system that is lossy has this problem. So again, another fundamental problem in computer science. Any other questions? Okay, so this relay attacks could be happening in many systems, by the way. It's not only the cars. Think about your credit card that can be used this way. Actually, there has been instances of attacks that shows that in Metro, your card can be relayed. That's why many people carry this kind of RFID secure. They put their credit cards into this kind of metal boxes because they're worried about these kind of attacks. I personally don't use them, but there are many friends that I know that they carry them because they're worried about these kind of attacks. So this is kind of like what we call relay attacks. The goal of the relay attacks is that you want to lie about the distance, right? So really, we're not lying about the values, or we're not trying to break anything. You're just trying to lie about where the signal is in terms of distance, okay? So generally, how do we establish this? So like, how do we actually, like, how generally these models works? And then we're gonna see how we can attack it. And then we're gonna talk about how do we defend it, okay? So essentially, this proximity is established based on measuring some physical distance, right? How do we do that? We're gonna observe some changes in the physical signals. For example, we're gonna look at the phase or amplitude or the time it takes and things like that to measure the distance. For example, I know that the phase, for example, if I send a signal like this, if I know the beginning phase, I can basically measure the phase at any point and I know where the signal is because I know the propagation of the signal and I know the initial phase, I can measure that. A more straightforward thing to do is I can measure what we call time of flight, okay? So time of flight is this, that I have a transmitter, I'm gonna send some signal, let's say I send a laser. I'm gonna wait for the signal to kind of like hit the object or whatever I want, and then it will come back, it will be reflected. I'm gonna have it RX, this RX could be on the same device or could be different device. I'm gonna measure how long does it take for me to send and then receive. And since I know the speed of the signal, for example, if this is light, I know the speed of light, then I can measure the distance, right? So how much does it take? And all of these kind of distance measurements equipment, including LiDAR, works like this, right? So you measure the time of flight, and this way you're gonna get that. The nice thing about this is actually it ties into some physics, right? So the attacker can never lie about the speed of light, or they cannot change the speed of sound, or things like that. So these are fairly, robust way of measuring time. Although the attacker can do other things to attack it, which we're going to discuss in the next few slides. So as I said, the first thing you can do is that you can rely on the strength of the signal. Okay. So for example, I know, let's say, there is a key fob here. Okay. There is an initial amplitude for the signal. I know that amplitude is usually a factor of squared with distance. So n is equal to 2, for example, in this case. So I measured the amplitude, receiving amplitude here. And based on that, I know how much is the distance between the remote and the receiver, right? So the amplitude is one way of doing this. Of course, this is there are obvious problems. So in theory, that's how you would measure it. In reality, though, is that this is the measurements that you have is only when there is no path loss. In other words, there's nothing in between the sender and receiver. There's a clear line of sight. There's nothing that's kind of attenuates the signal further. But if you have an object in between, then there will be a huge, loss in the amplitude of the signal. There are tons of things, folks that are working on, electromagnetics, signal and systems are very familiar with this. But generally, the idea is that you cannot fully rely on strength as, amplitude of the signal or signal strength as only one way of doing and measuring this. But it gives you some good approximation, right? Another thing that people have done is looking at the phase, right? So you send a signal, right? A phase of the signal, and then the receiver also sends another signal. You measure the distance between this phase and this phase, and then you can find the distance based on the difference between the phases. Okay, so for example, that if this is some multiple of the distance, the phase would be 0. And then every, I don't know, like 1 meter, there is a difference. Like, there is pi2 difference in the phase and so on and so forth. You can actually, measure that however you want. And this is more robust than distance because even if it goes through objects, usually the phase doesn't change, although that's also not true all the time, but it's a little bit more robust compared to just measuring the amplitude. Of course, you can measure both phase and amplitude, and that gives you probably a more robust way of measuring this. And lastly, as I said, you can measure the time of flight, TOF. That's actually the most robust way of measuring this. So the car, for example, sends the signal to the remote or other way around. The remote sends back the signal, and the device basically measure how long does it take for receiving this. The big thing here is that usually it's not like instantaneous, right? So you don't send and then receive, especially if these are two active devices. So for example, if this is a device that sends and this is another device that it receives, it takes some time to send the return signal, right? Because it needs to be modulated, it needs to make some decisions and then send a new signal. So usually we also have this little bit of delay in this process, which we usually call it TP or T of processing, or the processing time, okay? Ideally, you want this to be 0 so that you send it this way and then you can just measure it. In reality, though, that there is a little bit of processing. Again, the nice thing about this is that this is always the same. So regardless of what you have in between, the speed of light never changes. So you know that you can have a fairly robust measurements of time of flight. Questions so far? Good. And then the time of flight can be measured multiple ways. You can have the same receiver, you can have two different receivers, depending on how you want to measure it. But in both cases, what you need to know is this processing time. And then there is another problem that you might have, and that is what we call multipath, which, the signal that is sent might be reflecting from various different, objects and surfaces. So what you will receive may not be the same signal that you're sending. You will receive multiple signals from multiple paths. So for example, you may never receive the original signal, but you may receive the signal that's kind of going here, then going here, and then receive. So the distance that you're measuring may not be the exact distance that you think you're measuring because of the multipath. So there are these problems, and again, these are kind of like very deep into kind of antenna design and communication that is far out of scope of this class. All right, so given the system of the time of, let's focus on time of flight. How do you think an attacker can basically attack this? I already gave you a relay attacks, but let's see how creative it can be in terms of fooling the system. Anyone? How do you attack time of flight as an attacker?
You got the same distance that you are from the relay, right? If you are from the actual target device.
Yes.
Max distance.
Yes. So essentially, basically, the way the relay attack works is that if this is the transmitter and let's say this is your car, in reality, it should have been something like this, okay? But what the attacker does, the relay attack does, is kind of like sitting here. It takes this signal and it gives you this, right? So now you think that this signal is essentially the distance is this, right? So you're reflecting it faster than it should. And this transmitter will measure this, but in reality, it should have been measured this, right? So that's why we can see the distance is much lower. Yeah.
We can replicate the signal with different phases and at this one of them is the right.
Exactly. So you can also play with phase this way, right? So you can delay the phase, you can increase the phase, decrease the phase, and do these things, right? So that's like a very straightforward attack. And then anyone wants to suggest a defense for this. So now that I know that this blue one, I can basically intercept this blue whenever I want. Is there any solutions for this? Let's see if anyone else wants to say something. Yeah, go ahead.
Maybe the key can send two signals. The first one indicates the distance,
Mhm.
something like that, the time,
Mm-hmm.
the second signal, and then the second signal will be sent, for example, with that phase or that time after the first one.
So you, what the
So
second
the
one?
first signal will give, and it is an indicator for the phase that the signal is coming,
Mm-hmm.
and the second one is related to that, so.
Like, why can I, as an attacker, lie both? Like, I'll lie about what I like. Right? No, Brandon, so yeah, go ahead.
You could do some sensor fusion where you can also have like an additional maybe visual camera that like does some depth estimation, or I guess
Mhm.
like a different type of camera could be useful, but
Maybe, but you can also spoof that, right? If I can do one modality, the attacker can have another signal for the camera and maybe do something with the camera as well. And or if the camera works from the beginning, why don't I use just the camera, right? So if there is a camera that it works perfectly, I'll just use that. So if there is a magic answer, I'm gonna use that. But everything would be the same problem here.
Well, you're getting like two responses for like one send, right? So like, if you count like how many like responses you're getting for just like the amount of sends, it should like be like 1-to-1.
So what you're saying is that, at some point this red also will be coming back?
Yeah.
Well, I mean, what the attacker can do is that it can jam that signal, right?
Is it possible for the device to have like a tracker where the true other device is supposed to be? Maybe like for like a Tesla key, like. No.
If I know the answer, then I would know the answer. The whole problem is that I don't know where C is. If I know where C
Yeah,
is,
so
so
like have like a tracker where C is.
how do you do that? The attacker
Somebody
can
keep
lie
the
about that
signal.
too.
Like the car adds some token to the signal to like say, okay, I'm the one sending the signal.
Mm-hmm.
The transmission can verify it.
Okay. You want to say something too?
Would be like precise timing.
Precise
So-
timing, how
So,
does
like,
that help?
You like send the signal out and then it comes back, and it should have come back within this time frame. If it doesn't, that means it's been like been relayed, right?
Well, the idea here is that the attacker can even send it sooner than it should be. So even if you're measuring it, because you want to lie about you're closer to some distance, not you're further away from some distance.
But the relay they have to relay over a long distance, right? Oh, but then I see the key.
You can do it fast.
Yeah.
Yeah, one last thing.
I don't really understand how you can relay faster than the source can generate it, because isn't it that like there's a cryptographic system that doesn't allow you to like, generate whatever the messenger will generate beforehand. And then like there's all the nonce and stuff, so you can't like, it's like secure, and then every time it'll be different. So you can't just like grab what you're saying and like repeat it. I don't know.
That's true. Actually, that's what the solution is, and kind of what you said is also true. You want to say
I was
something?
gonna say like the car, after you send the open whatever, send signal to the car, it can send back like a challenge or something.
Mhm.
And you have to respond to the challenge in time. If
Exactly.
you don't respond in time, it means you've tried to relay it.
Mm-hmm. Yes. So the answer is like we actually converged to an answer. So all of your answers are kind of true. So the answer is kind of along these lines that it shouldn't be an arbitrary signal that we send so anybody can respond. It should be something that only the receiver, the true receiver, can respond. Okay. So this way, the attacker cannot just replay this, because this return signal should only be generated by the true owner of the control. How do we do that? We do this kind of challenge response paradigm. Okay, so what is a challenge response? The sender sends a challenge. Think about it as a random sequence of numbers, and the response should be some specific value based on that challenge. Think about it as like the simplest thing could be the encryption of that challenge. Okay. Who can encrypt this challenge? The one who has the secret key. Okay. So if I don't have a secret key and I have an antenna, I cannot do anything. Okay. So that would be the main thing, that no one in between can kind of like respond and just send this back. Okay. So based on this, we're gonna have this system that that is secure against just this very simple way of responding. Okay. But that's one part of the challenge, right? So that's only one thing that, okay, I cannot respond it faster than this. But remember that relay attacks can still provide this response, right? So, but this response now, again, another thing that we have understood out of this discussion that we have is that this response can never be faster than this, okay? So in regular systems, so let me show you this one more time. So this is your transmitter. If I just send a vanilla signal and then just wait for this signal to come back, and then if the actual receiver is here, the attacker can intercept this and send this back to me, right? And they can lie about the distance. And we said that this is a very bad idea, okay? So in order to fix this, we're gonna say that the attacker cannot do this. The attacker can only relay the whatever response that is coming from the receiver, because the response that is coming from receiver includes some token or some secret or some nonce include and some secret that only receiver can generate. But even with this, we have to be careful, because the attacker can basically relay this as well. And this is where the notion of time comes into the play. So now things that you said earlier make sense, that we only rely on the response if it's within some time frame. Okay. So this is what we call distance bounding. Actually, I have. So the idea of distance bounding is that not only I check the response, okay, I need to make sure that this has the signature, has the nonce that I'm thinking, but also I need to measure the time it takes for it to arrive. Okay, why? Because I know that the attacker cannot respond faster than the true receiver. Okay, so I can create some bound through my distance and say that, okay, my remote controller only works if I know that if I send the signal and receive it, it should take this amount of time. And the way they can actually work is that you can actually measure this. If I have you can actually measure this using some formula like this, right? So you know the distance is the time for you to send and receive plus some processing time, right? So there is some processing time as well, times the speed of light. So this is t times c gives you the distance, right? So x is like, time, x is t times v, just a very basic form, okay? So this way I'm kind of bound the distance. First, I'm going to make sure that the system cannot be lied about. Not everybody can generate the signal. And the second thing is that the response cannot be generated at some time. If I have these two, then I'm going to have a secure distance bounding system. Right? Any questions? Yeah.
But if there are like obstructions in the way of the signal, block it. And like someone.
So the question is, what if someone blocks? Well, if someone blocks it, you're never gonna get the signal back. If you don't get anything, your system just doesn't work. So this is still not secure against denial of service. So the attacker can always jam your signal and then your remote won't work. But that's at least much better than your remote just randomly unlock your car at will, right? So basically this means that you just keep clicking and nothing happens. Good. All right, so let's go back and then actually go step by step. All right. So I gave you the time of distance estimation. So as I said, the obvious attacks for this is two things that the attacker can do. The attacker can do what we call delay and relay, which means that they can play with the phase, or they can do amplify and relay to kind of mimic the behavior of the the amplitude. So if amplitude or phase are things that you're relying on, both of them can be manipulated with by the attacker. Okay, and there are like ways to do both, and attackers, there are multiple attacks that shows that if you're just relying on strength or phase, this can be attacked. Yeah.
Yeah, so like in all of this situation, there should be some control in your car key to understand all of these.
Yep.
But what about the situation where like RFID, like like a hotel lobby key or a credit card or something? You cannot have a controller on a card.
There is no control on the car, but there is a control on the reader. So in your car, so all of these algorithms are implemented in your car, not on the remote. Remote basically is just this dumb device. Actually, remotes do have controllers, but think about it as it's just send the signal. All of these things are happening on the car side because car is the one decides that whether this has to be locked or
I'm
not.
saying this because let's say some encryption code was sent by the car key to the car. Then car encrypted that code and then again send it back to the key. So first they have to verify that it's the same code based on the encryption that they're.
No, so this is kind of like two. So the car sends a request. So these signals, the initiator of all of these is the car, not the key. Okay, so when I'm showing you this is your car. This is not your key. So the key is only says its presence to the car. So initiation is by the fob, but this process is by the car, not the key. But again, many of these key fobs, they do have microcontrollers and all of that. So they're not that simple. But yeah, like an RFID, only thing that it does is just send you. So it's actually receive a challenge. So most of them are actually passive, right? So the way it works is that you send an actual signal, some energy, it gets demodulated and sent back. And so that's how it works. Yeah. Oh, you had a question? No. Okay. Cool. So I can do amplify and relay or delay and relay, and I can get. There's also some terminology that might be useful for you to know. There's different types of distance fraud, actually. There is what we call distance fraud, then there's one called mafia fraud, there's another called terrorist fraud, there's also called impersonation fraud, and distance hijacking. There are subtle differences between them. For example, distance fraud, obviously P, the prover. So there is like a verifier and prover, right? This is a challenge response. Verifier is the one that you trust and verify things. Prover is the one that wants to prove itself, prove its distance. So in this case, the fob is the prover. It wants to prove that they are in some vicinity of the car. The verifier is the car, is the one that you trust, okay? So in distance fraud, the prover, the key fob wants to try to prove that they are closer to the verifier than they should, right? That's the entire goal of the attack. Mafia fraud is a fraud where adversary tries to prove that prover P is close to the verifier. So same goal, but the difference is that the adversary kind of relay things. So this is the relay attack, basically. This is just a regular distance attack. This is what we call a mafia fraud, which is there is a mafia, there is a third party that tries to kind of do this, okay? The terrorist fraud is there is kind of like two attackers at the same time. There is a malicious prover, and there is also an adversary that tries to help the prover in this case. So it's kind of like the more advanced version of a regular mafia fraud. Impersonation is mostly, there is another device A that tries to stay on P. So this is different than P itself trying to lie. This is like there's another device that you kind of try to replicate the original device to try to lie about it. And then the distance hijacking is that you're trying to hijack the distance. Again, kind of like similar in terms of distance fraud, but this is like, again, a very particular case of distance fraud. All right. So as I said, how can we fix this? This is what we call distance bounding that I described. Essentially, distance bounding is a cryptography protocol. Remember, I told you about primitives and protocols and said protocols are methods that use these fundamental things that we discussed in the class, including digital signatures and message authentication codes and all and that, and try to build a system on top of it. So distance bounding is one of those examples. Okay, so it's a cryptography protocol. What it tries to do is that it tries to establish some trust about a physical device P and show that it's impossible that P is further, that is closer than what it says it is. Okay, so we are not that much worried about this P prime here, but we are very worried about this P prime here. I don't want a scenario where device says that they are distance M, but in reality, they are a further away distance, okay? So that's why we want to bound the distance and say that, okay, it cannot be closer than this. That's what we want to achieve with distance bounding, okay? Any questions here? Okay. And this is like another example. It's okay that, you know, these things are a little bit further away, but we want to make sure that it's not possible for the attacker to lie about the distance. All right. So we kind of discussed this also within that Q&A that we had. And the first thing that we said is that we need to have some form of a specific response, right? So we cannot just kind of like, you know, rely on some vanilla signal, some signal that anybody can return, because an obvious attack to this is the adversary just return this from some smaller distance and say that, okay, this is the result, right? So this is kind of like what we call the mafia fraud, right? So there is an adversary in between that kind of lie about the actual distance by returning the signal as soon as possible, okay? So what do we do to fix this? We're gonna use, instead of using the n, which, you know, the actual signal, we're gonna apply some functions to it. So we're gonna compute f of n, okay? So if I send some signal, I'm expecting to receive some specific functionality based on what I send. So that's the important part. If the response is not based on what I send, again, the attacker can pre-process and pre-compute this response and send it back to me. So this process has to be challenge response, has to be two-way, such that I send some challenge, you compute some response over my challenge, and then send it back to me, okay? So how do we do that? As I said, you can use decryption, you can use MAC, you can use digital signatures. And the key thing here is that only the receiver and the transmitter, or the prover and verifier in this case, has that key. Again, distance bounding will be broken if the adversary has the key, okay? So this is similar to any other cryptography measures. If the adversary has the key, these things won't work. But if the adversary has the keys, they have bigger problems, such as like every message you send and receive is also decrypted and so on and so forth. Okay, so the same thing with cryptography, and then we assume the same things that we had in general encryption, decryption mechanism. For example, the algorithm might be fully known to everyone, including the adversary. Everything about the system is known except the secret key. And usually these things are symmetrics. They're not asymmetric, but they could be also asymmetric. Okay. So great, right? So kind of we fixed this issue that we had that said that, okay, I'm going to send you something, you encrypt it, send me the encryption, or you sign it and send me the signed version, and that's going to fix the issue. And this is kind of like the original idea of distance bounding, but unfortunately there are tons of problems, real problems in distance bounding. The main one is that when I send something, the receiver, the prover has to compute, right? It has to encrypt or compute the signature and all that, and then send back the result, right? So there is some delay for this, and this delay could vary based on the device, could vary based on the condition. Even worse, if there is some form of a network or channel in between, and then, you know, condition of the channel or network changes, there is additional delay. So in reality, not only remember I told you that I basically rely on two things. T2 minus T1 should be smaller than some threshold. And also f of nv should be equal to some expected values. These are the two conditions that I'm going to check. But since I have this additional delay, now my system has to kind of be a little bit more, flexible, because now I need to accept that there is going to be a little bit more delay, and the real distance is the distance that takes for this value to be received plus that delay. Okay, but the big problem there is that now the adversary can actually use that delay. If the adversary can compute the response so fast, now they have that extra time that we kind of assumed for the delay to lie. For example, people have shown that 1 millisecond extra time for adversary means about 150 kilometers, about 93 miles extra distance. So you can see that how big this number is. 1 microsecond means 150 meters, right? So even tiny bit of delay, and the fact that the adversary can use this delay in their benefit could basically lie about 150 meters. That's a lot, right? Especially for a car. So we need to have very, very, very small processing delay. Okay. So how do we fix that? There is this algorithm called BC or Brands-Cham. There are these two famous researchers that long time ago they actually introduced this very simple algorithm. This is called the distance bounding protocol or Brands-Cham protocol. So the idea is very simple. The idea is that since this response computation is very, very sensitive to delay, we need to make this computation very, very simple. Okay, so what they do is that they make this as simple as just XORing 2 bits. Okay, the second thing that they do is that since this is also very delay sensitive, let's actually compute the average. So let's not do this one time. Let's do this thousands and thousands of times. This way I'm looking at the average number. Okay, so here's what they do. Okay, so we have a verifier and a prover. This is an asymmetric, but this could be also symmetric. The idea is that the prover pick a message, okay, and then send this message to the verifier as well, okay. The verifier, what they do is they pick a long vector called challenge, could be zeros and ones, okay, just 1 bit. So this challenge has, let's say, has 1,000 bits, okay, zeros and ones. What they do, and we call this C. What they do is that iteratively the verifier can send these bits one by one. So it's going to send from C0, C1, C2. Going to keep sending this. So sending the CIs. The prover, what they do is that they basically compute the MI XOR with CI and send RI. Okay, it's just 1 bit again. Okay, so one XOR. The key thing is that only the verifier and the prover knows the M, because M is the secret between them. And then what we do is that on the verifier side, we're going to run the clock here, and we're going to stop the clock here. Okay. And then we're going to measure this. So we're going to measure this, let's say, 1,000 times. And then what happens is that there's at the end, this is an additional step to make sure that the response that I'm getting is only from the prover. Is the prover also signs this response that it computes. So not only send it bit by bit, but then compute the whole response and sign it with their secret key. Okay. So this way, the attacker cannot generate this on the fly because the signature has to be based on what the original sender sends, right? So this way, we make sure that this is indeed came from the sender, not from an arbitrary user. Okay. So why this is helpful? Because as you can see, this process is extremely fast. right? And the second thing is that if there are some changes in the network, since we are looking at the average behavior is kind of like average out those transient behaviors. So even if one of these taking so long, the average, if the number of times we send this is so high, the average would be low. Okay, so that's how this thing works. Any questions?
So this requires both of them to already like share a secret key,
Yes,
but this is only to verify essentially the distance bounding.
to verify the distance bound. Yes. So basically, what the verifier does is measure the time for the response. The time for response should be lower than some threshold.
You do all this just to protect against replay.
Yes.
Yeah.
And then again, this one, the original one, they don't need to agree on the secret key. This is a public cryptography system. So as you can see, the signature is based on the public key. Okay, so basically all the verifier needs to know is the public key. The private key is with the prover. So that's why it's a digital signature. Otherwise, it would have been a MAC. Okay, but if it's a MAC, then it's a symmetric key, then you can just compute the MAC. Perfect. Let's have a quick break, and then we're going to talk about some newer version of this, and then we're going to move on to the next topic. Let's continue. All right. So kind of the summary of the DC protocol is that you repeat one activity many times, and that activity itself is very small. So this way, you kind of fix this issue of the computation delay. And then there are two things that you do, right? So you make the response simple yet dependent on the challenge. And then you make the challenge itself unpredictable by creating it at random. And then you sign the final response to also show that the communication between the sender and receiver is bounded by some security. Otherwise, the attacker can impersonate, right, the receiver, the prover, and then try to respond. So you don't want that to happen as well. Okay. And this is kind of like what is happening, right? So you try to make this delay very small, such that the processing time is not a big factor in your computation. So what are the challenges in real systems? So this distance bounding has been something that has been quite a lot of work in literature. Still an active area of research, although it's like with lower pace. But there are many papers that is coming after this original one. If you're interested, definitely go and check them out. There's a nice survey that I'm gonna I put into the slides as well. There's one key challenge. I'm just gonna talk about one of them, but there's a few others that if you're interested, you can take a look. The main one is that in real systems, still this kind of, even if I told you that response computation is just an XOR, in reality, this is not just an XOR. It's actually has to go through the entire RF chain, right? So it has to be received and amplification and filtering and detection and demodulation and analog to digital conversion, then becomes a bit. And then, yes, this is just maybe picoseconds of computation, but then it again has to go through the whole analog process to be modulated and amplified and so on, and then send, right? So in reality, we say bits, but in theory we say bits, but in reality, this bits needs to be actually sent and received by some radio protocol, right? And I need to do this very quickly. So this is not something like delay of this part is actually so large that it's kind of overpower or overshadow this kind of small delay of this part. Okay, so what can we do instead? There is this paper, very interesting paper called channel selection. So the idea of channel selection is that XOR could be as simple as I received the RF signal, either I reflect it or I don't reflect it. And this means you know, sorry, but I reflected in both cases, but I reflect two different signals. So I have two different signals. I receive a signal. I either reflected, I reflected NV or NP. So the two different signals that I can reflect based on the signal that I'm receiving. Okay, and this way I can do everything by I can do everything in the analog domain. I never actually do an XOR. I never compute it in digital world and so on. So another thing that you can do is that you can actually send it at two different frequencies. So I send the same signal, but there are two different channels, and I send it at two different frequencies. So I send it at like 2.4 and 2.41, depending on the answer that I want to send. So if the receiver can look at two different bands, you can see which frequency is present in which band, then they can know what is my answer. And again, this will be based on the challenge. So it's not like, I'm sending random signals. I'm based on the challenge, I'm going to respond in one of those two channels. Okay. And the nice thing about this is that it's purely analog. So it's just a simple comparison and analog. Yeah.
How do you respond in the analog domain? How do you do the challenge computation with the analog domain?
So think about a pulse, right? So I send like a small pulse into two different frequency bands. So I either send a pulse in, let's say, frequency F1, or I send a frequency in F2. That's all I do.
But then on the receiver side, you have to know which one to reflect.
Yeah, so that would be as simple as, whatever you receive. So there are these multiplexer in the analog domain that you can select. Yeah. So you can do that. It's a switch. There's actually an analog domain there you can do even multiplication and addition. So, but yeah, it's fairly simple. Any other question? Yeah, so this they actually build their I think this is the paper. They actually build it in the real system with the RF modules and all that. So if you're curious about that, you can take a look. Anyway, so essentially what it does is that we want to make sure that the receiver cannot lie about their sensor. We tie this into some physical aspects of the system. That is, the speed of light cannot be modified, cannot be faster. Based on that, we create this cryptography protocol that basically sends this random challenges, and the response will be based on these random challenges. And combination of this physical design, the rule of the nature, and the design of the cryptography give us a system that's very robust. And these type of systems are systems that you want to build in security domain because essentially they're tying something that you can prove. There's also, as I said, this problem is not fully solved. There are a whole bunch of other problems that came after this, including what if the attacker can somehow predict the challenge and pre-compute the response? So in this case, then they can lie about it. So there are different things that people have suggested, and as I said, this is kind of like a attack defense scenario. Yeah.
What would this look like for networking protocols? Is this used for trying to prevent relay attacks for networking protocols?
For networking, you can do the same. The only difference is then the analog domain would not work. You have to rely on the fact that your packets are within some distance. So for example, that in order for this packet to be received, it has to be within this distance. Otherwise, if you're talking about internet, so this won't work because the notion of distance in the internet is. But for example, let's say that local server, local communication within UCLA's Wi-Fi network should be in order of, let's say, tens of microseconds. If you want to communicate with Asia, that has to go through a server West Coast server, from West Coast server to Asia server. So that would be in order of hundreds of milliseconds, right? So these things you can prove that based on based on the ping time, you can, for example, know where the origin of the signal is, right? But it's a slightly different problem because in the network, there's other delays that you have to be worried about.
Yeah, there's no like fundamental constant, so you have to send out that page.
Yeah, there's no speed of light kind of thing. Yeah. But there might be other concepts. For example, as I said, you know that it's impossible for you to connect to AGIA faster than, let's say, 100 milliseconds. Because it has to go through the servers, and there's like the smallest amount of delays in these servers are this much. Unless like someone come up with a cable from here to AGIA, which is probably not possible. This is a survey in case you're interested. Any final questions about distance bounding? This was just one example of how some information, physical information can be fooled and can be detected as well. So kind of like both attack and defense, which was quite interesting. All right, so let's talk about AR/VR as well. So the reason that I'm talking about AR/VR is that, you know, these kind of, whatever you want to call it, some people call it extended reality, some people call it, you know, virtual reality and so on and so forth. The different, depending on what you use. What is happening is that these devices are becoming more and more integrated in our systems. And there are tons of attacks that could happen in this system. The reason for it is they are also, you know, has access to some important secrets about us. For example, many of these devices, you use it to type. And as you're typing, for example, you need to sign into your Facebook account. You need to, like, you know, search web and all that. So you have to type, and then this typing could reveal some secret. And then typing generally is much slower in VR compared to regular typing. Yes.
You mean typing is like doing this in the air, right?
Yes. Typing like in the virtual domain. And then usually the keyboard itself is much bigger than what you have in the system, right? So, but typing is just one example. Generally, we might have this problem. So the one that I want to talk about is what we call keylogging. Although, as I said, there are other attacks to the VR as well. So the idea of keylogging is that if someone is interacting with VR or AR, in this case, let's say talk about VR, so like Meta Quest or the Apple Vision Pro, what they'd see is like, you know, a virtual domain, and they start interacting. So for example, there's a giant keyboard and they start typing. And now we are doing this, what we call a keylogging attack or bystander attack, that someone in the real domain will see your interaction with the VR domain. And now the question is that as you're kind of doing this typing, can they figure out what you're typing and what you're doing? Okay. So the third model is that, you know, for example, the simplest one that we are going to talk about, the first one we're going to talk about is based on the camera. So we assume that the adversary has no access to the hardware or software of the headset. So headset is clean, it's completely secure, but all the observations are made externally, okay? Observations can be in the private space or a public space. If it's in the public space, imagine, for example, you're in the airplane and you're using your VR device to work. So you're kind of typing and there are other people who will see you, right? Or it could be in the private domain. For example, there is a security camera in the room, or there is, I don't know, your neighbor can peek and look through the window and see this activity, okay? So you kind of like think about like a situation like this, that you're sitting in your living room or standing in your living room. You may or may not use your controller. There are attacks that shows that the controller can leak. There are some attacks that shows that, you know, just by fingers you can attack. So you might have a system like this. Some of these may exist, some of them may not. But generally the idea is that can I actually, by just looking at the frames, let's say I'm recording this video from this camera, by just looking at your movement, can I figure out what can be typed? And this is actually a paper that we recently published, like last year, and we show that this is actually indeed possible. Okay, so the pipeline looks something like this. So there's someone that, kind of like, clicking. We show that from different angles of the camera, we can record the video. Then what we do is that we go through kind of like 5 stages. The first stage is locating the fingers. I'm going to explain how do we do that. Then we detect 2 things. We detect the click detection because when you're typing, you have to kind of do this. Like whenever you go to a particular key, then you do this, and then you do this, and so on and so forth. So we do the click detection. We do some feature extraction. Based on that, we locate the location of the keyboard. And then once we locate the keyboard, then your relative distance between your finger and the key would be the key that we are detecting. You had a question, Jacob?
Yeah, so what's the difference between this and like just recording someone's regular keyboard?
No difference.
So, like, what is this like showing them? Is it showing like that like people think that VR keyboards are more secure, but really they're not?
2 things. One is regular keyboard, usually it's more concealed. So first of all, there's tons of attacks on keylogging on keyboards, especially in 90s and early 2000. There are many papers that shows that, oh, you're in a coffee shop, you're using a laptop, boom, I can find your keys. There are attacks that shows that you can actually type your cell phone again. Back in the day that ATM was a thing, there are lots of attacks called shoulder surfing that, or you're do something on your on the ATM, someone recorded like CCTV camera and so on. So similar ideas. This is just another example of those. The only thing is, yes, you're unaware of the fact that this is happening. And the second thing is that as these devices become more and more widespread in public places, then the opportunity of the attack grows because you won't bring your like big keyboard in, while you're walking, but it's very likely that if you start like using these glasses and all, and then you start typing on the street, then people can figure things out.
I'm like record you and walk by.
Yeah, exactly. Yeah. Mhm. Any other question? Yeah.
Like what if like if they were like the user was typing like a password or something, they just like randomize the keyboard every time, so it's like harder to track.
True. They can, if you randomize the keyboard, then it's much harder to track. That's actually the first thing that comes to mind. The problem with randomized keyboard is that it's terrible for the user experience, right? So these things are already very slow, and now imagine that every time you press, like the keys are randomized. Another thing that, for example, we also looked at is like you can change the size of the keys. That can help as well, but generally anything that if you mess up with the keyboard, generally, that will negatively impact the user experience.
Okay.
So yeah, but yeah, there is some defense for it. All right, so let me show you this quickly step by step. So in order to kind of detect the position of the person, we use MediaPipe. How many of you have used MediaPipe before? A few, one. So MediaPipe is this deep neural network machine, open source by Google. It gives you something like this. So you give them a frame. It gives you 23, 21, 20, yeah, I think 23 points of your body. You probably have seen this in videos that, there is like a 3D guy with like, weird like lines. This actually gives you all of these points. It's very accurate, actually. Very nicely can find all these points. Okay. What we are kind of mostly interested in is like these points here and these points here, because these are the fingers. Okay. So that's the step number 1. You just take the frame, you feed this frame to MediaPipe. It's going to give you the X and Y of all these points. Okay. The second thing is that you need to know when a key has been pushed, okay? Because that's the point that you want to know. So if I do this, you want to know when I do this, and then locate these kind of 1, 2, 3, 4 points. And this will be basically giving you the location of your finger at that point. If I can then overlay the location of keyboard, then you know exactly where my hand was, right? So you know the exact key. So how do we do that? Essentially, the key idea is we look into these 2 points, okay? Because there's 1 point for here and 1 point for here. We saw that whenever the distance of these 2 are very, very small, that's when this thing happens, okay? So if someone kind of doing this, it's actually a false positive in our system. But the reality is that if someone kind of using it, they're not gonna do this unless they're clicking something, right? So if you look into this basically what it does is giving you 2 points. As you can see, this is the distance and this is over time. And you see this big drops, and then this is for left hand and right hand. So the assumption is that the victim is typing with both hands. So you can clearly see that the distance of these 2 points kind of drops, and these are clearly the points that the typing is happening, okay? The others kind of go up and down because your fingers kind of move, but there's like a very clear point that you can see that there's a huge drop, okay? So this is the time that you know that the clicking is happening. So you have now the exact time of the clicking, okay? Then the third thing is that you now need to figure out where the keyboard is in this space, because you have a camera there and I'm doing this and the keyboard could be in the virtual domain. I don't know exactly where the keyboard is, right? So I need the projection of my hands to the virtual space. If I can do that, then I have the answer. So how do we do that? We kind of try various different things. What we eventually figured out was kind of like all these points of your shoulders, your head, and then your fingers will give you, all these together will give you the kind of some location of the keyboard. So for example, in this example, you see this blue, kind of light blue is the actual location of the keyboard in this particular case, okay? So we kind of like did some feature extraction and some machine learning in order to locate the positions of the keyboard, okay? The last thing that we did was that now we're kind of trying to figure out what we found, that this keyboard locationing is not very accurate because, like, you know, there are people that are taller or shorter. They're like, you know, you can like type it like this, or you can type it like this, or you can type it like, there's not much consistency. So what we did was trying to see that how we can kind of reduce the search space. So what we found was that our algorithms was kind of 2 key away. So like what it does is that it could be correct, or it could be 2 key to the left or the right or up and down, okay? But then another thing that we figured out was that, you know, based on the location that they're kind of clicking, it would reduce the search space based on the cases. So for example, if I do, I think L, E, and N, for example, if there are there are 3 different rows, then I know exactly where these, like, you know, I can remove the top row because I know that, you know, it's impossible that there is a row above this. So if I know, for example, there's only 3 rows, then I can eliminate the top row. And the same thing with the left and right. So if I see enough, then I can eliminate the cases. So I showed this with, like, you need some time to see different keys, and then eventually you can figure that out. So we did that, and then eventually we get the exact location of the key, and then I know the finger, I know when the clicking has happened. I found exactly where the key is. We actually test this in real world with MetaQuest and Amazon Blink, 4 meters away. We look into different angles when the camera is exactly in front of the victim, when there's 45-degree and there's 75-degree. If you're interested, you can take a look at the results, but looking at various different things like accuracy, the work length, combination of brute force and our attack, the user dependency, if you have a taller or shorter person, and things like that. Some results, for example, you can see that with top 100 number of guesses, you can actually get close to 80%. So if the words between 16 to 12 characters, with 100 guesses, I can find the exact word that's been typed. If I get lucky, sometimes with even one guess, about 60%. So much better than random guessing, of course, because random guessing a 12-character word takes a humongous amount of time. We also look into word length. So as the length goes higher and higher, your accuracy will drop, right? So this is kind of, I think, the largest, and this is the smallest. So That's also another thing. That's why, like, longer password might be a better idea in some cases. We also look into location of the key and randomly removing it. Again, I can share the paper with you, and you can take a look at it. But just what I'm trying to show you here is that as something as simple as just from looking at the frames, I can basically figure out what key has been pressed in the virtual domain. And in any part of this attack, I never actually touch the device itself. So no software changes, no hardware changes on the device itself. So this is completely external. Questions?
So I'm guessing like when you have the headset on and you like look around, it probably changes where the keyboard shows, right?
Mm-hmm.
Is there a way to like kind of project where the keyboard is at all points where you're facing?
Yeah, well, so when you're moving around, the body will move with you, right? So the idea, that's why we kind of use the shoulders and the points as well. So you could, at any point, you can be anywhere. So you can also do this and then type. And technically this can work. But of course, we had some assumptions such as, you're not going to move too, like when we were doing the results, we didn't like do this. Because the assumption was like, if you're using it as a regular user, you're going to probably have some consistency, right? Especially when typing. Yep.
Can you defend against this? Like, do you come with any good defenses?
Some defenses are like, randomizing the keys, randomizing the size of the key, but realistically, you cannot defend it.
What if instead it says like on your screen, it says type your password, but in the middle of these two letters, put like this letter.
Yeah, you can do that. Again, there are things that you can add some form of a different behavior. You can even like, if you like move the keyboard a little bit, that will also mess up this. You can also, I don't know, like turn and then type. You can do these things. But yeah, generally this is kind of more of a raise of awareness about that. Probably if you're like, I don't know, in the metro, don't probably like type your passwords, right? So that's not a good idea. So this is not the only attack. There's actually quite few attacks. Another interesting one is using microphones. So this is actually a recent paper in NDSS. They show that with the iPhone microphone, they can record your activity. That one you need a controller, because basically what they record was the clicking sound of the controller, not like your fingers. But they show that they can actually find this very easily. The nice thing about this one is that it doesn't need line of sight, so it can actually work across the wall as well. Yeah.
Hey, how do you tell the password just from the acoustic?
So what they show is that like the sound of the click is different because you need to
like
move your
left, move left, right?
no. So this controller is like for MetaQuest. Like you have to move it, right? So you have to, like, if you want to click like A, you have to do it here, and then the other words you have to do it here.
Amplitude is different.
The amplitude is different, yeah. Even for like regular keyboards, there are attacks that shows that with acoustic you can figure it out. Same idea.
The sound is outputting from the headset, right?
No, it's not outputting from headset. So you're just using it, yeah. So it's like him typing and you listen to it, right? So same way. Any other questions here? But if you're interested, this is the paper called Eavesdropping on Controller Acoustic Emanation for Keystroke Inference Attacks in Virtual Reality. This is a very recent paper. A very cool paper, this one. This is like very recent, actually, done by my colleagues at UCLA. This one shows that all these things that said can happen in the virtual domain itself. So you have this kind of metaverse, kind of like, smaller, people. They've shown that if someone typing in the metaverse, the other person with the fingers can actually figure things out. So you're not also safe in the metaverse. Although this one needs a little bit more, so it's not just the location of fingers. They also show that it needs to kind of demodulate the packets. But it's kind of interesting to see that you think that you're in complete, like, even if you don't do the actual typing in real world, or like you are in a room, nobody else seeing you, in the virtual domain, people might see you. So just keep that in mind as well. This paper called Remote Key Logging in Multi-User VR Applications. If you're interested, take a look. It's actually product of UCLA. Yeah.
Wait, but it's like very easily detectable, right? Like as a software developer, you can say that, oh, whenever my user is typing something, make it so that I see them.
True. Yes, you can do those things. Again, any of these defenses kind of eats up your user experience. So like if like this person is kind of like suddenly disappear, you might like wonder what's going on. You might think that, oh, this is a network connectivity issue, right? But yeah, maybe you can also, I don't know, like pixelate the fingers, do things. Yeah.
And I feel like this attack could be like more like just beyond password. It's like someone's like maybe like name or address, besides like just like a password prompt, right?
Well, I mean, in this domain, you may also need to type in your password. So it's still, because these are like metaverse, I was working, like, I remember I was interning at Accenture many years ago, and they had their group meetings was in metaverse because Accenture at that time was like pushing for metaverse. So like there was like the manager actually coming, and then so there actually was a big thing for them at that time, especially like for Meta also. It's kind of dying down a little bit, this metaverse thing, but still it's happening in some cases. Any other questions? Cool. So just to summarize, the reason I wanted to talk about this is that, this augmented reality, virtual reality, extended reality is growing for sure. And the main difference between them and regular systems is that they are much more closely integrated with the physical world, that many of these attacks that we talk about, the sensors, the faults, the side channels, is actually much more efficient, unfortunately, more effective in this domain. So we have to be very, very careful. All right, so last thing I want to talk about, we don't have much time, so hopefully we can finish this soon, is what about ML? I don't want, specifically in this course, I don't talk much about machine learning. Reason for it is that we have also another course on specifically on machine learning and security and privacy, which is happening with this course at the same time, which I think some of you are taking it. If you didn't, consider taking it in future. But since, machine learning is on the rise and closely integrated with many systems, including like, IoT systems, I want to quickly talk about it as just a small module. If we have time, maybe in week 10, we kind of revisit this. So what are the fundamental differences between just a regular system and a machine learning enabled system when it comes to sensor security? The main thing is that most of you are probably familiar with adversarial machine learning. So this is something that somewhat kind of accidentally has been discovered many years ago. Like not many, actually 10 years ago. And machine learning many years is like 7, 8. But what happened was the original authors was trying to make their like diffusion model, like, your generation models better. So they're trying to see if they add a little bit noise to the system, can they kind of remove that noise and generate better pictures? But they found very interesting thing. They saw that if I have an original picture that is a panda with some confidence, if I add tiny bit of kind of random noise, so this noise is kind of very small, and I add this pixel by pixel to this original image, the resulting image will look like this, which is visually very similar to Panda. But if I feed this into some machine learning classifier, for example, like a regular AlexNet at that time, or like a deep neural network, it will be labeled as, for this particular case, as gibbon, as another animal. And as you can see, the confidence level that this is a gibbon is 99.3%, which is quite interesting and very surprising, right? So what does this say? It says that things that are visually similar for you, for human eye, has been perceived by machine learning very, very differently. And this kind of was the birth of this entire field of machine learning called adversarial machine learning, which tons of people start thinking about, okay, if this is that easy, I can actually add this noise to many different things and fool the machine learning, okay? And fooling machine learning is very, very helpful for the attackers, right? So there are things that they can do. So, for example, people have shown that if I have an audio signal that says, how are you? If I add this tiny bit of noise, just again, time series signal, it will be open the door. Okay. The top one again, it's a duck. I add the noise, it will be a horse. So for example, the bottom one, I can basically what I do is that if I can have a recording and then add a little bit noise, I can open the garage door by just, if this is a machine learning system, of course. There's another very famous attack called physical patch attacks. And this is also when it came out was like a big deal, was that people actually showed that if they add this small patches to this traffic sign, so for example, this is stop sign. So this is the regular stop sign. They actually go and design these patches and they add it. So these are actually physical patches. These are not digital patches. If you add this different patches to the stop sign, actually the classifier think now that this is a yield sign and this is a speed limit sign. And there's also this physical attacks has been growing significantly. There are lots and lots of these papers so this one is kind of like visible. Then newer attacks, they kind of like distribute this and like there's tiny bit here and tiny bit there. So like, instead of like having this, there's kind of like things like small things here and there. And then you kind of overlay this to the stop sign and it works. So there are many attacks in this domain that shows that, you don't need an expensive laser or, you don't need to have a big speaker and kind of shoot it to the drone, but in fact, you can actually have smaller patches. And if this drone is using machine learning for path planning and decision making, this can be fooled very easily. How many of you were familiar with adversarial machine learning before this? Okay, so it's quite known for many people. And then if you remember, I told you that, essentially, this is the kind of attack scene. Yeah, question.
How do you know what noise to put in there to make it have that output?
I'm going to actually talk about that. Yeah. In a few slides, I'm going to show you that. It's an optimization problem, actually. So it's like same as learning problem. So if you remember, I told you that sensors could be at the physical domain, analog domain, digital domain. Machine learning attack can happen on all these three stages as well. So the ones that I showed you just now was the physical domain. I add a patch to the stop sign. The car goes, has no idea this is manipulated stop sign, thinks that this is a yield, just go and boom, it crashes with another car, something like that. So that's kind of the goal in the systems. So generally, if I want to summarize, machine learning and sensors facing similar issues in the physical domain, analog domain, and digital domain. The goal usually is calling some form of a malfunction, could be confidentiality, integrity, availability. The fundamental difference is that things that we have discussed so far are mainly rule-based. And in rule-based systems, you at least have some idea why things go wrong. In machine learning, even the designer most of the time does not know why their system works or doesn't work, right? We have the same problem with the machine learning originally itself. So it's not like it's 100% accurate system. In rule-based systems, without the noise, typically the system is 100% accurate. With machine learning, it's not. So there's actually much less known about the key reasons that the system doesn't work. Why the system can be full, and then I'm going to answer the final question. The reason that the machine learning can be full is because machine learning fundamentally work on decision boundaries. So essentially, the idea of machine learning most of the time is that you have, I'm just showing you a very simplified version, that you have a 2D space and you have two classes, the green and the red. What machine learning really learns is finding this decision boundary, right? So, it tries to draw this black line. Usually we have dimensionality. So for example, this is like multi-layer, so that it learns that if it comes with this kind of decision boundary, then it has 100% accuracy, right? So the reason that fooling works is that, as you can see, there are samples that are very, very close to this decision boundary. So if I change the X, Y, Z of this point slightly to the bottom and right, it will actually pass the decision boundary so that its classes will be flipped. Okay. So the reason that these things exist is that there are samples inevitably close to the decision boundary, like the screen point. All I need for this to be misclassified is that I add a little bit to the right and a little bit to the top, and then this will go here, and now it's flipped. Okay. So this is kind of like what we do with adding this small perturbation during the prediction. And then I showed you how we can do that. We can do it with physical attacks and all that. How do I find and how do I create this adversarial samples? That's a question that's been asked. This is essentially an adversarial, this is an optimization problem. What is the criteria? I want to find minimum amount of perturbation such that it flips, it changes the outcome. Okay, so think about this, that I don't know the decision boundary. I have a point. What I do is that I start adding small perturbation in different directions. So for example, I start add a little bit here and have this new point. Then I check this point and see what is the class of this point. If I see it's the same, I might go into this, I might continue in this direction. Or I might decide to go up or to go down or to go left. How do I decide where to go? Usually I use the loss function. So I see wherever the loss is increased, that's the direction I want to go. So it's opposite of what you want to do in training. In training, you want to go to the direction that the loss is reduced. In adversarial training, you want to go to the direction that the loss is increased. Okay, so it's a gradient descent, same gradient descent that you use for training, but the opposite of the direction. So you do the minus of the loss, and that's what you do. You go to that direction. Okay, so that's like as simple as this. There are tons of these algorithms. The famous one is fast gradient descent method. There are also other iterative method that does that too. We don't have much time left. I'm going to talk about this kind of final things in on Wednesday before the beginning of class. Any final question? All right, see you guys on Wednesday. Oh, by the way, new computer assignments is posted. Computer assignment 2. The second thing I posted is the appointment for your projects. Whoever is ready to say what they're gonna work on, please go and make an appointment with me. The link is on the website. It's 10 minutes. You just have to explain what you're gonna work on. So I have it in my list, and we can discuss. I can give you some pointers as well. Okay, so do that ASAP.